Okay, if there is one kind of angle type that is going to be crucial to understanding the way the various terms of this unit, the various ways circles are solved in this unit, it is going to be inscribed angles. We really need to have this one down. So an inscribed angle is defined as an angle whose vertex lies on the circle. Remember what that means, that the vertex would be on the circle's edge then, and whose rays both intersect the circle. So as you look at a circle with a point on that edge, if you connect from that edge out to another point in two different directions, you essentially make two chords, so that the angle has to be formed by two chords, then you end up with what's called an inscribed angle. So to name two inscribed angles, what you want to do is locate a point on that circle and start there for the vertex, and then you can work your way through the rest of it. So if I want to get angle, let's say this an angle at A that I want to call an inscribed angle, I cannot just say angle A, but I could say angle DAC. Angle DAC would start on the circle's edge, go out to a vertex on the edge, and land on the circle's edge again. Angle DAB would work. Okay, I could also use B as the vertex. It only told me to do two, but if I'm looking for some others, ADB would work. Angle ADB or DAB. Or DBA rather. ADB like this. Or ABD that way. So there's several of them in this particular diagram. This word subtend. Subtend is an interesting vocabulary term that will come up frequently. Also the word intercept. Intercept and subtend are synonymous in this sense. Two inscribed angles can intercept or subtend the same arc, and that will happen if they both have rays that intersect the circle at the same points. Now by subtend, what we mean is that if let me just grab a quick highlighter here. If I start with D and I go out to A, and I go out to B, that's an inscribed angle. And what it ends up doing is subtending this arc here. And so arc AB is considered a subtended arc or intercepted arc by angle ADB. Think of it like the top of a snow cone. If the two chords make the sides of the cone, I know it's not a perfect cone, but if those two chords make the sides of the cone, this would be the shaved ice or the scoop at the top. Okay? So as we look at that, is there more than one angle that can do that? In this diagram, I don't have two that are ending up at AB, but let's say I had done the AD arc instead. Let's look at this arc here. If I follow A back to a point and D back to a point, then maybe I'm looking at it as this snow cone, right? But could I also have made a snow cone going back to, say, B from both of those points? Sure. So since there's two different snow cones that are formed, and I keep using that term, but I think it works visually. If there are two different snow cones that are formed on the same arc, then that same arc has been subtended by two different angles. Okay. So there's a special relationship between the measure of an inscribed angle and the measure of the arc that it intercepts. Let's just quick review the exterior angle theorem, because that's what's going to be used here to prove it. So the measure of an exterior angle in a triangle, one that's formed by an extension line, is going to be equal to the sum of the two remote interior ones. So if I'm talking about angle 3, that's going to be equal to the sum of 1 and 2. Alright, so that fact, along with properties of circles, will give us the fact that an inscribed angle will be 1/2 of the measure of its arc. So let's prove that. In the diagram of circle M, we want to show that angle BAC, which is angle 1, is half of arc BC. Okay, so the first question that's going to lead us down this path, why is triangle BMA isosceles, and what does it tell you about angles 1 and 2? Well, this triangle here is isosceles because we have two radii. AM and BM are both radii, so then angle 1 must equal angle 2 because base angles of any isosceles triangle are equal. So based on that fact, why should it be true that angle BAC is half of BC? Now if you think you can reason through this, go ahead and do that. Why is angle 1 half of arc BC based on these two facts here? Alright, so let's start with angle 3 and talk about what that's equal to. Angle 3 is equal to arc BC. And that's because that arc is subtended by a central angle. So central angles will be equal to their arc measures. We talked about that in the last lesson. Right? And so, since angle 3 is also equal to angle 1 plus 2, because of the exterior angle theorem, angle 3 is an extension, so it's equal to the sum of the two remote angles. I can take those two equations and mash them together. And also at the same time, so I can say that, well, first off, let's take this here. Let's take this angle 3 is equal to angle 1 plus angle 2. Okay, so backing up there, angle 1 plus angle 2 is the same as two angle 1s. Think about why that might be. We just said that angle 1 and angle 2 are equal. So having a 1 plus a 2 is the same as having a 1 plus a 1, which would be two angle 1s. So since arc BC is the same as angle 3, then arc BC must be two angle 1s. And so angle 1 is half of arc BC. All right, so going back to the diagram, since angle 1 goes out to arc BC and angle 3 goes out to BC and angle 1 is half of angle 3, angle 1 is also half of that arc. So going forward, if you have a snow cone that starts at the circle's edge and not in the center, the arc on the outside is going to end up equaling double the angle, or say the angle is half of the arc. It goes both ways. All right, so let's look at some more of that. Exercise 2 is a special case where one of the rays of the inscribed angle was a diameter. Now we had that where the central angle and the inscribed angle were both coming from the same line. But the relationship will always hold no matter what. So in this diagram, we want to show that angle BAC is half of arc BC with the diameter involved but not really, because the snow cone arc is connecting to these two chords here and not the diameter chord. So based on exercise 2, what can we say about angle BAD and angle DAC? Well, based on the previous exercise, BAD has to be half of its arc, and DAC has to be half of its arc. Right? So I have those two facts there based on what we just said about an inscribed angle. So using our answer from that, prove that this angle is in fact half of that arc. All right, let's take a look. Okay, so angle BAC is going to be equal to the sum of those two angles, right? If I add this angle plus this angle, I get the whole thing. All right. Now, we just said that angle BAD is half of an arc and CAD is half of an arc, right? So I'm just replacing those. That's legal algebraically. And so it's equal to half of the sum, because algebra allows us to factor out common terms. And so it's half of the sum. And so it must be half of the whole arc, because arc BD and arc DC are adjacent. So if I add them together, I get the whole arc BC. So since each of these angles was half of their arcs, the total angle must be half of the total arc. That's the way to summarize that. Okay, so the relationship between inscribed angles and their intercepted arcs is going to come up fairly frequently. In this circle, you can see an example of this with a quadrilateral based at the center. So in circle O, angle MOP is 118. Explain why angle MNP, which is the inscribed angle, has to be 121. So let's look through this. If angle MOP is 118, then the arc must also be 118. So the arc that I'm talking about here is this one from M to P, that minor arc there. That arc is 118 because its central angle is 118. Central angles and arcs are equal. Inscribed angles are half of their arcs. So there's a difference there between those two things. Major arc MP is got to be 242, so that's going the other way, right? And I really should have named that. Well, I don't have another letter out here, so I guess I could mark it. But major arc MP goes more than a semicircle. So that's going all the way around this way, and pardon my missing the circle there. It's actually fairly terrible. So that's a little better. All right, so that major arc is 242 because I'm just subtracting the 118 from 360. So hopefully that's pretty easy to understand. So angle MNP is this angle right in here, which goes out to M and P and subtends this major arc. So if that major arc is 242, the angle must be half of that because it's an inscribed angle subtending a 242 arc. Right? So this major arc out here is 242, which means the angle in here must be 121. All right, much more work with inscribed angles in class.